If the event appears genuinely random, does it mean we are simply missing information, or is nature unpredictable at its core? For centuries, the greatest minds in physics believed that chance was nothing more than an illusion of human ignorance. In classical mechanics, every action is governed by strict laws of cause and effect, forming a deterministic universe. Consider a simple coin flip. To human eyes, the outcome seems entirely random between heads and tails. Yet if we know the initial force, thumb angle, torque, air resistance, and height, the trajectory is completely predictable. Epistemic uncertainty arises from missing data, while ontological uncertainty represents intrinsic randomness in the laws of physics. This concept of apparent chance due to hidden data is called epistemic uncertainty. In 1814, Pierre-Simon Laplace pushed this philosophy to its ultimate mathematical boundary. He envisioned an intellect that knew the exact position and momentum of every atom in the universe. Laplace calculated that an intellect with total knowledge of every particle could foresee the entire future with absolute certainty. For Laplace Demon, the past and future were equally present. Randomness was simply missing information. Consider weather forecasting. Atmospheric systems exhibit chaotic dynamic sensitivity to initial conditions. Small measurement errors grow exponentially, making weather seem random over long time frames. Three classical systems show apparent randomness: chaos in dynamical systems, statistical mechanics in gases, and complex coin trajectories. Statistical mechanics reinforced this view by treating thermal motion as averaged microscopic movements. Temperature and pressure emerge from trillions of individual collisions governed by basic physical laws. Enter the quantum revolution, where the deterministic foundations of classical physics were shattered. In the early 20th century, physics encountered subatomic phenomena that resisted classical models. Radioactive decay presented a striking puzzle. A single unstable nucleus decays without external triggers. We can calculate the half-life of 1 billion atoms with extreme mathematical accuracy. Yet for one specific atom, physics cannot predict whether it decays in 5 seconds or 5,000 years. Heisenberg's uncertainty principle sets a fundamental limit, proving position and momentum cannot both be precisely known. The Copenhagen interpretation, led by Niels Bohr, claimed this uncertainty was an absolute feature of nature. Quantum systems are described by wave functions evolving deterministically via Schrödinger equation. However, upon measurement, the wave function collapses into a single definite state according to the Born rule. Einstein famously proclaimed that God does not play dice with the universe, refusing to accept intrinsic chance. Albert Einstein strongly opposed this view, believing quantum mechanics was incomplete. He argued for hidden variables, unmeasured parameters that determine quantum outcomes in advance. Under local realism, physical properties exist independently of observation, limited by the speed of light. This created a historic standoff between Einstein's local realism and the non-local probabilities of quantum mechanics. In 1935, Einstein, Podolsky, and Rosen published the EPR paradox paper. They showed quantum theory implied spooky action at a distance, which they viewed as absurd. For nearly 30 years, this remained in philosophical debate with no experimental test. John Stuart Bell transformed this philosophical clash into an experimental test of physical reality. In 1964, Northern Irish physicist John Stuart Bell derived a mathematical inequality. Bell proved that if local hidden variables existed, measurement correlations must obey a strict bound. Quantum mechanics predicted a correlation value up to 2 times square root of 2, violating this bound. This created a clear mathematical test between Einstein's local hidden variables and quantum theory. Cyrelson's bound proved quantum mechanics can achieve correlation values up to 2.828, far exceeding classical limits. In 1982, Alain Aspect performed the definitive experimental test using entangled photons. Aspect's results violated Bell's inequality, confirming quantum mechanics predictions. Subsequent loophole-free tests in 2015 eliminated remaining technical doubts. Decades of tests culminated in the 2022 Nobel Prize for experimental proof of quantum entanglement. In 2022, the Nobel Prize in Physics recognized Alain Aspect, John Clauser, and Anton Zeilinger. Their experiments proved local hidden variables cannot explain quantum correlations. This forces a profound choice: abandon locality or accept intrinsic randomness. Physicists proposed alternative interpretations seeking to restore determinism through non-locality or parallel realities. The de Broglie pilot wave theory saves determinism by introducing explicit non-locality. In pilot wave theory, particles have definite paths guided by a universal wave function. However, this requires instantaneous communication across the universe, violating relativistic locality. Alternatively, Hugh Everett's many worlds interpretation removes collapse entirely. In many worlds, every quantum measurement branches the multiverse into all possible outcomes. The global multiverse evolves deterministically, while observers experience branch probability. The three main quantum interpretations offer radically different answers: Copenhagen chance, pilot wave non-locality, and many-worlds branching. Another exotic idea is superdeterminism, suggesting particle states and detector choices share hidden history. Superdeterminism saves local determinism, but sacrifices experimental free choice. Let us examine how information theory and computation distinguish pseudo-randomness from true quantum randomness. In computer science, pseudo-random algorithms use deterministic formulas to simulate randomness. If you know the seed value, every future output number can be predicted with complete certainty. True random hardware generators exploit quantum thermal noise or photon beam splitter arrival times. While software pseudo-random algorithms rely on secret seeds, quantum generators produce truly unpredictable physical entropy. Kolmogorov complexity defines randomness as an incompressible string with no shorter algorithm. If a pattern cannot be compressed, it contains maximum information density and zero redundancy. In information theory, true randomness achieves maximum Shannon entropy with complete incompressibility. This paradoxically means true randomness represents maximal information rather than missing information. Why does our macroscopic daily experience deceive us into believing all randomness must be missing information? Why does our intuition insist that randomness must mean missing information? Because in human-scale environments, quantum decoherence averages out quantum effects instantly. Trillions of particle-environmental interactions destroy quantum superpositions in fractions of a second. At cosmic and human scales, quantum decoherence washes away quantum superpositions into an illusion of classical determinism. Every coin flip, roulette spin, and weather forecast obeys classical epistemic randomness. At these large scales, randomness is indeed missing data, exactly as human intuition suggests. However, zoom into fundamental subatomic scales, and that classical intuition breaks down completely. The verdict reveals a dual reality. Randomness is missing information for coin flips, but fundamental law for quantum particles. So to answer the core statement, is randomness always just missing information? In our daily macroscopic universe, yes. In the underlying quantum reality of nature, no. Thank you for watching this deep dive into quantum foundations and the true nature of physical randomness.